the, the content. Yeah, anyway, today we will start looking at superconducting qubit. The first thing we will look at is, this is a typo. Sorry for that. This should be Cooper pair box. What is Cooper pair? What happened to superconductor? Very good. When you go to superconducting state, two electron pair together, they become a Cooper pair. Okay, so this is called Cooper pair box. You need to wait until the end to appreciate more, but let's just go ahead. So let's go back to the DiVincenzo's criteria for quantum computing. We did that for spin qubit already, right? And earlier we actually already discussed about this qubit-specific measurement capability. We already discussed how to do measurement. Because of the project, I went ahead to do the measurement of superconducting qubit states, right? We have the resonator coupled to a qubit. The resonator frequency will change depending on the states of the qubit, whether it is up or down. So now actually I go back to the most fundamental one. Do we have a scalable system with well-characterized qubit? Meaning, do we have a two-level system? Earlier we said that an LC tank is not a good qubit because it's not a two-level system. It's a multi-level system. It is very easy for you to go from state 1 to state 2 to state 3, right? So that would be a problem. So now we are going to look at this. And then later we'll look at the qubit control, 1 qubit, 2 qubit gate, and to see that you have a universal set of quantum gates. Regarding the coherence time, we assume it is good enough. We won't spend too much time on this. Okay? So let's look at this. When you look at this picture, right, what do you recall? We just learned LC tank a few classes earlier, right? It was a capacitor with an inductor. With that one, we form a simple harmonic oscillator. We did not go through the derivation, but we showed that its equation is exactly the same as a mechanical oscillator. So it is also a simple harmonic oscillator in this case. In the LC tank, you can have the fault states from 0, 1, 2, 3, 4, 5. Right? What's the meaning of 0, 1, 2, 3, 4, 5? What does it mean? What's the meaning of states being at n, capital N? Do you recall? What's the meaning? How about in a mechanical simple harmonic oscillator? What's the meaning of 0, 1, 2, 3, 4, 5? It represents the quantum of energy, right? You have 0 quantum of energy, 2 quanta of energy, 3 quanta of energy. And we show that in LC tank, you have the same status also, right? You can have 0 quantum of energy, which means you have 0 photon. 1 quantum of energy, you have 1 photon. 2, you have 3. Okay, so now we want to study this structure. This structure is exactly the same as LC tank, except we replace the inductor by a Josephson junction. Right? This is JJ. It is drawn in this way because a JJ is just a capacitor. What is the structure of a JJ again? How do you make a JJ? It's just a capacitor. Two superconductor as the metal, and then the middle is the insulator. So it's just a capacitor. That's why you have a CJ. You do have a capacitance, right? And then this we call the bare Josephson junction, which has the Josephson junction effect. Okay, obviously we all forgot what it is, right? So let's recall JJ, what we learned earlier. It tells us that the voltage across JJs equals to the reduced flux quantum times d phi dt. where phi is the phase across J. So across the junction. So I'm showing you here, right? This is Josephson junction. Let me move this one to the left. Yeah, it is showing here. Across this junction, I have a voltage Vj. I also have phi, which is the phase difference between that two metals. Right? I can call this Vj. The voltage across this Josephson junction is going to depend on the rates of change of the phase across this junction. If you forgot, the meaning of phase is what? They have superconducting qubit. They have superconducting metal, right? And for superconducting metal, we already derived that it is a army marching in coherence. You describe it with a global wave function. So every wave function has a phase. This is the phase difference between the two metals on the top and bottom of the JJ. Right? So if you forgot, you need to take this for granted for now and go back to study. Reduced first quantum is a constant, so I can bring this in. Right? And I would like to define a quantity just called flux is equal to the phase times the reduced first quantum. Okay, so basically what I'm saying is that I define a quantity that is phi equals to reduced flux quantum, right, times the Josephson phase, right? And this whole thing, you look at it, I'm basically saying that Vj equals to d phi dt. So this flux, this one, it acts like flux. Again, Josephson junction doesn't have magnetic field. We only pass through the current, right? But it has this relationship that the voltage across the Josephson junction is equal to a quantity d phi dt. And this d phi dt is, this phi is just a fundamental constant times the phase difference. So the phase of a Josephson junction act like the flux in an inductor. That's all I want to say. It act like the flux in an inductor. Right? Of course, it's very profound if you go deep to understand all these things. Probably I don't know much more than you. But the main point here is that now you accept that for JJ, it has a flux associated with it. This is not a real flux. But this flux acts like magnetic flux. D flux dt equal to the voltage. And if you forgot that voltage equal to d flux dt, then you either accept it or go back to study the fundamental circuit again, right? So here I introduce this one, right? If this is the case, then it means, as we remember, flux is the generalized coordinate. So this is the generalized coordinate of Josephson junction. Okay, so somehow we associate, right? There's no coordinates whatsoever. But when we studied the LC tank, we did have a generalized coordinate, which is the flux in the inductor. And now through this equation, we also claim that, right? We did not prove that, we claim that this phase times reduced flux quantum, which we call it phi, is the generalized coordinate of JJ. Any questions? This is a very big transition, but any questions? Now, if you accept that, then what is the Hamiltonian of JJ? Basically, although Hamiltonian is the total energy, right? We did not prove it, but we just get it as it is. What will be the energy of this JJ? You have a charging energy, Q square over, no, sorry, not for JJ, for the whole circuit. I said the wrong thing. Okay, maybe let me make this clear. The total, let me even don't call it how, just say the total energy of the circuit. Now, how about we recall first, right? We recall for LC tank. For LC tank, what is the total energy of an LC tank? Is equal to the capacitive energy Q squared divided by C plus the inductive energy, right? Li squared. Or here I don't have the cheat sheet, but I think I'm correct. Or it is equals to the flux square divided by L. Are you okay with this? This is what we learned last time in the LC tank. Now, if this is the case, then the total energy of the circuit is going to be what? I still have the same capacitor, right? So I should have 1 over C, 1 over Q squared, 1 over 2Q squared divided by C as the capacitive energy. And then I have the Josephson junction energy. Why this is the Josephson junction energy? Because we derived it last time when we studied Josephson junction. I hope you remember. Okay? Now I can further simplify it. I say this is just equals to this one. Okay, I did two modifications. I want you to tell me what are the difference. What's the difference between these two terms? I dropped EJ. Why I dare to do that? Very good. Because EJ is a constant. And for energy, we can always shift the constant because there's no physics there. You're just increasing the energy. You only change your global phase. But again, it's not going to affect your physical observation. So this is a very important point you will see often in the literature or other textbook, right? We draw EJ, which is a constant. What is the other difference? I substitute phi, which is the phase, Josephson junction phase, Josephson phase, by phi divided by phi naught dash, which is just this definition. Okay? Why do I want to do that? Because now I represent the Hamiltonian in two variables. What are these two variables? What do we call these two variables? Now this is just equal to h of q. Maybe I better write h of phi and h of q. What are they? What is phi and q again? When we're talking about this Hamiltonian mechanics. Not exactly the conjugate. Are they? I don't know if you call it conjugate. So maybe you. No, you're right. I'm wrong. You are right. Conjugate variable, because this is like coordinates, right? And q is like momentum. So you're right. Conjugate. Of course, you're right. I'm wrong, right? So this is important because we say in Hamiltonian mechanics, you need to represent them in the generalized coordinates and generalized momentum. Now, I understand this is quite a lot, but the point is I want to help you understand some of the transition. After all, if you accept this equation, then that's it, right? So you agree the Josephson junction energy is negative EJ cosine phi over phi not dash. And this is just 1 over Q squared. With this, what can we do? What is the next step? Do you remember? What is the next step when we find the Hamiltonian of a system? What do you do if you want to do quantization? What do you do in a simple harmonic oscillator? After we find that it's half kx squared plus half m omega squared promote the operator. Thank you. Yeah, so you will promote operators. So actually it is very easy. You just need to add the hat to it, right? Promote two operators. So the result will be h hat plus q hat squared divided by 2c minus ej cosine phi hat divided by phi not dash. Okay, and this is the equation or the system of linear equation you need to solve. And naturally, if you forgot, right, what is the commutation relationship between these two guys? What is that? Phi and Q? IH bar, yes. If you go for the math, then you will get a quantization. But for Qubit pair box or for this Josephson junction, for this superconducting qubit, it is easier if we work in the so-called number and phase operator instead of the charge and phase and flux. So charge and flux are the conjugate pair. Number and phase are also conjugate pair, as what you just said, right? So what is the number operator? First of all, number operator is lowercase n hat. So this is very important. It is not capital N hat, which is the Fock state. Again, I just ask you what is the Fock state? It refers to what? What's the capital N we have been talking about for simple harmonic oscillator? Again, what is that? It's the number of quantum, right, of energy. Right, in this case, maybe number of photons, right, for the LC tank. Is that clear? So what can be the value of N? What can be the value of N? We proved last time also. Thank you. But here, this number operator lowercase n refer to the number of Cooper pairs tunneling across the junction, the JJ, right? It basically saying how much Cooper pair tunnel across this JJ. Sometimes we can say it is the extra number of Cooper pair in this box, in this island. Right? If you have one extra Cooper pair tunnel through it, then you have one extra Cooper pair here, right? So what is the possible value of small n then? Well, I add one pair is plus 1. I don't add anything is 0. I add two pair is 2. What else can be the value? What other value is possible? Say again. 2 to infinity. Can it have negative value? Huh? Okay, looks like you want to define. Yeah, what do you say if what? Uh-huh. Mm, mm. Oh, we will do that, but not now. However, now it's like he's saying that I only have positive number of n, small n, because I'm counting how many tunnel through this junction, right? But from current perspective, can you get negative current usually in your circuit? What's the meaning of negative current? Or positive, just the direction. But you're also right. So you can have negative n. It means that you actually have less excess Cooper pair in the island or tunneling in the opposite direction, right? So this is very important. Don't mess up. So n can be between negative infinity and infinity, right? So when we work on the floor space, when in your homework, right? Remember you try to apply the lowering and raising operator. You only apply to 0, 1, 2, 3. You cannot have negative 1. But if I try to construct the space in this excess group pair, then I can have negative. So in your matrix, in the homework, you go from 0 to infinity. At one side is fixed, right? Then you dot, dot, dot all the way to infinity. But here, if you write in the basis of the number of excess Cooper pair, then you go from negative infinity to positive infinity. Make sense? Right? So this is the thing you need to be very careful. And then now go back to what you just said. How is n related to Q? N is the number of excess Cooper pair, right? Then it must be equal to negative Q hat divided by 2e. Because I'm talking about the number of Cooper pairs. So if I have 2 electrons, then I should have negative 2e of charge. Then I have negative 2e divided by 2e times negative 1 equal to 1 Cooper pair. Right? Or think in another way. The total charge due to 1 Cooper pair is 2e. E is positive, by the way. Okay? It's n times 2e times negative 1. Make sense? If you have 2 Cooper pairs, then you have 4 electrons. And totally you have negative 4e. Right? That is the total charge. So that is how you relate the number operator to the charge the charge operator. So you can guess now, n probably is the generalized momentum of the new conjugate pair. If I want to call it generalized momentum, right? So there will be another quantity, of course, that is phi. This is the phase of the Josephson junction, right? So what is the phase? We already say this is phi divided by phi naught dash. But it's important to realize now that we actually now unify everything together. So this phase doesn't need to be a Josephson phase. You can even have an inductor in your circuit. You just take the flux divided by this reduced magnetic flux quantum. Then we also call it phase, right? And this is the phase operator. Okay? And with this, maybe I should write this down first. We have this relationship, phase. The commutation between them is I. No, right? No H bar. This one you need to be very careful for this equation. There's no H bar. Okay, phi n equal to I. Okay, so with this, then I can write down the Hamiltonian. The Hamiltonian from the last page was H equals to half Q squared divided by C minus EJ cosine phi hat divided by phi dash 0, right? Let me check if it's correct. Yeah. And now I'm going to substitute what I just learned. This is 1/2 because Q equals to negative 2En hat square, right? I substitute it. The second one, actually, I just revert back to the face. Minus EJ cosine phi hat. Then I further simplify this to 4EC n hat square minus EJ cosine phi hat, where EC equals to E squared divided by 2C. What's the meaning of E squared divided by? Did I say it wrong? No, I said the wrong thing, I'm sorry. 2E squared divided by C. This is the charging energy of one electron. So basically, if you put one electron on top, what is the energy when we put one electron in a capacitor? It's half. No, sorry, I say the wrong thing again. Not one electron, right? Should be one Cooper pair. This is the charging energy of one Cooper pair. Why? Because what is the energy when you put a charge on a capacitor? It's 1/2 Q, but it's Cooper pair, so it is 2E instead of E, right? Q squared divided by C. So this gives us 2E squared divided by C, right? That's why this is the charging energy of I keep saying the wrong thing. I'm sorry. This is wrong. Half. So what I'm saying here is correct. This is the charging energy of one Cooper pair. Okay, my cheat sheet is messy. This part is correct. So I also want to change a little bit. I call it ECC. Okay. A lot of confusion. So it will be clear after I make it clear again, right? So what is the EC here? EC is actually the charging energy of one electron. So it will be half. It will be E squared divided by 2C. The charging energy of one electron. Right, first, let's check if this is correct. If you substitute this to here, you will get what? You will get E squared, 2E squared divided by C. That is exactly what we have here. Right, this is EC. It's the charging energy of one electron. If you put one electron across a capacitor, what is the energy? 1/2 times E squared divided by C. Okay, don't look at this yet. Is this clear now? Is it? I know it's sorry for the mistake, but this is the charging energy of one electron. Any question? No question? But often you also see people will use EC for charging energy of one Cooper pair. That was the mistake I made earlier. In my book, I call it ECC. So it is 2e squared divided by c. Why? Because if you have a Cooper pair, your charge is 2e. So it's half 2e squared divided by c. So you get this 2e squared divided by c. So when you read the literature, sometimes you will see the Hamiltonian as ECN squared. Then it means that they actually are referring to the charging energy of a Cooper pair. Right? But now here's 4 ECN squared. Then it is referring to the charging energy of one electron. So that is something I want to make it clear. So let me remind you again, for this, phi and n are conjugate pair. Okay, so what have we done here? I know a little bit confusing. We repeat what we did in LC tank, and we come up with this Hamiltonian. We have the generalized coordinates as Q, generalized coordinates as flux, and then generalized momentum as Q, or use flux and Q as the conjugate pair. But we foresee it's not going to be convenient. We want to convert it to number and phase operator. Number is referring to the number of Cooper pairs, so it's going to be Q divided by 2e times -1. Phase is just the flux divided by the reduced flux quantum. And they obey this commutation relationship. There's no H bar, however. And then we convert this equation to this form. Now the Hamiltonian is a function of the number operator and the phase operator. And then I get confused. I confuse you by this EC, the definition, but it's just definition that you get confused. Please read it again to make sure that you understand. But you need to be careful when people talk about charging energy. Make sure whether they are talking about the charging energy of one electron or one Cooper pair. For one electron, the charge is E squared. For one Cooper pair, it's 2E squared. That's why you will get different answer. Okay? Any questions? So what we have done so far is we come up with the Hamiltonian in quantum form for this, what we call the Cooper box, Cooper pair box. Okay. So now we want to solve it, right? We are not let's see how. Let's first understand is. My God. So looks like I squeeze everything here. Okay, so this line is not used. Okay, now we look at the Hamiltonian. So let me write down the Hamiltonian again. H hat equals to 4EC n hat squared. And this should be easy to understand because, yeah, it's proportional to the square of the number of Cooper pairs, right? Minus EJ cosine phi, yeah, this is Josephson junction energy. Now I can expand this to this. The first term is still the same, but I don't like the second term because I want to use some equations. So here I convert cosine into e to the power I phi. Again, this is an operator, plus e to the power negative I phi divided by 2. This is just a general expression, right, for cosine, how you express cosine in terms of e to the power I phi. Because e to the power I phi equal to cosine phi plus I sine phi. So cosine phi plus I sine phi plus this one, you will get negative I sine phi, they got cancelled. This one, you got 2 cosine phi divided by 2, then you convert it back to cosine phi. Okay? The reason I want to do this will be clear later. Okay? So I want to find the matrix element of it, because if I can find the matrix element of H hat, then I will be able to solve the Schrodinger equation, right? right? So what I'm finding is, I would say H-M-N, which is what's the meaning of H-M-N based on what we have been using so far? For element, Mn, what does it mean? Thank you. In row M and column N, right? So this is just a pure number. It can be complex, but it's just a number, right? So how do we find HMN? We do this. And here I actually need to emphasize, now we work on the N basis, the number operator basis, right? So you go from negative infinity to infinity. Now, let me recap this one. Remember, yeah, you can have any equation, but you cannot express them if you don't specify the basis you want to write. It's just that you have a concept. You cannot write it down. Until you decide to write it in English, in Japanese, in Hindi, in Russian, whatever, then you can write it down. So H is just the concept. Yeah, the physics is over there. But how do I describe it? I need to determine what basis to write down. Make sense? Another example is like my height. My height is a physical quantity. But I cannot tell you the number until I determine which unit to use. In feet, or in SI unit, in cm, or in meter. They give you different numbers, right? So this is important, right? Although you already know, but it won't be overemphasized. Right? The importance of it won't be overemphasized. When I want to write in Mn, it means that I'm using I need to choose a basis, and now I'm choosing the N basis. And basically here is telling me that what is the elements on M row and N row, okay? But it corresponds to what? It really corresponds to number for row N, right? But now this one is actually infinity. Let me write down the matrix. It is like this, right? You really don't know what it is. But this one will go to all the way to negative infinity. This might refer to 0. This might refer to 1. And then you also go all the way to positive infinity, right? So you have a matrix that has infinite number of row and column if I want to describe the system correctly, right? So Mn, and here, of course, this is the N basis, right? So Mn represent that. So once I have this, then I can just apply it to my matrix. Then what will I get? It will be 4C, 4EC, and then M, N, hat square, N, right? And then minus EJ divided by 2. And then I have M, e to the power I phi hat, N, plus M, e to the power negative I phi hat, N. What am I doing here? It's just that this is a number. I apply bra on the left, so you apply M to left. It will hit this operator, N hat square, it stop there. Distribution rule, so you will hit this operator, stop there, so you have M from the left, and apply the cap from the right. That's why all the operator will be sandwiched by Mn, which makes sense because they are just matrix. Right? The element, Mn element for the final matrix is just equal to this operation of the elements of other matrix. Now the difficulty is how to evaluate this, okay? Now, But here is this. I'm going to give you, we are not proving here. You can look at the textbook on how to prove it. If you apply e to the power I phi to n. Now remember, maybe, I don't know if you can appreciate this. We have two conjugate operator. N is the generalized momentum. This is the generalized coordinate. This is an operator. This is a state. This is the eigenvector or eigenstate of the number operator. So you apply this operator to the eigenoperator of this one, right? You will get this. You will get n plus 1. And if you apply negative I phi hat to n, you will get n minus 1. This is completely given, right? You have not proved it. You can look at the book on how to prove it. But the point is, if you apply this to the number operator eigenvector, you are going to increase it or decrease it by 1. So in some sense, this looks like the raising and lowering operator, but not the raising and lowering for the Fock state, right? Not for this capital N, which is the number quantum of energy, but for the number of Cooper pair, excess Cooper pair in the island. Any questions? You from your... Yeah. Okay. Okay, so let's do it one by one, right? Let's look at the first term. So that is purely math. What is 4 EC m n hat square n? What is this if you evaluate it? So maybe I did not say it very clearly so far, right? What is the meaning of n? This n is also the eigenvector of n hat. Okay? I did not say that. Maybe I should have. Right? So this n eigenoperator, n is equal to q divided by 2e. Right? But it is all, its eigenvector, we call it n, right? So we are using the eigenvector of n hat as the basis. Maybe I should have said that. So I chose a basis, right? I have the right to choose that. I chose n hat, n, right? But I forgot to tell you that this basis that I chosen is the eigenvector of n hat. Okay, so then what will be this? What will this be? If you cannot see it, let's look at this carefully. N hat squared is just n hat times n hat operate on n. Again, n is a what? N hat is what? Is it a number, a vector, or a matrix? What is n hat? Is it a number, vector, or matrix? Matrix. So this is just matrix times matrix, right? What is n times n? N hat times n vector. What did I tell you? What's the relationship? What is this guy to this guy? It's the eigenvector of n, right? So if you have eigenvector of n, you apply to it, what do you get? Scalar n times the n hat. Then I do it one more time. Again, this is the eigenvector, right? So this one is going to be 4 EC n squared mn. Right? Because I apply it one time, another time I got two numbers multiplied together, n squared, and then I have mn, right? What is mn? What is the meaning of this symbol again? What is it doing? Inner product. What do you get? Can you guess what's the result? Huh? It's constant, yes, but depending on Mn, what are the values? Or 1. Because we're talking about the basis, I did not tell you, this is also orthonormal. Okay, so then you will get E 4EC n squared delta nm, or in other words, it is 4EC n squared if m equal to n, or 0 if m not equal to n. That is the answer. Then what it means? It means for this term, you will only get non-zero along the diagonal. Right? And its value is 4EC squared, 4EC n squared. For example, if you are at 1, it is 4EC1 squared. At 2, it's 4EC2 squared. Right? It only appears on the diagonal term. Make sense? Yeah, so we say we don't need quantum mechanics and much math, but eventually this is actually what you learn in quantum mechanics, right? Okay, but I still need to evaluate these two terms. But you probably know how to evaluate already, right? Because I give you these two equations. When e to the power I phi applied to n, it will give me what? N plus 1. E to the power negative I phi applied to n, you give me n minus 1. Right? And then you do the inner product. So let's do this one by one, right? So the second term, we have m e to the power I phi applied to n. And based on the equation from the previous slide, this gives me n plus 1. Right? So what is the value of this? The inner product between m and n plus 1, what do you get? Something like before. What are the possible values? 0? Okay. I mean, the probability will be 0 or 1, right? So it is like what you say, when it is equal to 1, when m equal to n plus 1. Otherwise, this is 0. Now remember, what is m? M is the row and n is the column. It means your row number need to be plus 1 over the column number. So that means it is actually go to one diagonal shift from the diagonal. Right? How to say that? For example, this is the diagonal, right? And now you say m equal to n plus 1. For example, this might be m equal to n plus 1. Am I right? Row. mn. When m equal to n plus 1. Yeah, I'm right. So this might be n plus 1, and this is n, right? For example, when you have 0, then here it is 1, right? So you shift down, right? So this row, this term is going to fill up this diagonal row, right, for this one. Okay? And similarly, for the third term, I need to go a little bit faster. It is m e to the power negative I phi hat n, which is equal to m n minus 1. Again, we use that equation. And now this is equal to delta m n minus 1. So if this is green, it's going to fill up this off diagonal. So the whole thing is that this Hamiltonian, although it's infinite by infinite, but everything everywhere is 0 except these 3 diagonal rows. Right? So based on this, I can write down the Hamiltonian. Now this is a little bit daunting, but you should be able to appreciate. So what is the Hamiltonian? Hamiltonian equals to first, I hope you understand this. M equal to negative, how about this? Let me say that. The Hamiltonian equals to the outer product of each term, and then times the element. And then you sum over n and sum over m. Right? So maybe you feel this is too much, but just think about this again. We have done that before. How do you construct a matrix? All you need is to try out the elements of the matrix, right? This is the element, MHN. This is the element. But where to put it? You put in the outer product of MN. Right? If you forgot, let's give you, I hope that, for example, let's say 2 by 2 case, right? Let's say 0 H1 times 1, times 0, 1. What is 0? 0 is 1, 0, right? And what is 1? 0, 1, right? This guy gives us what? It gives us 0, 1, 0, 0. Maybe I don't need to do this, right? So each of this outer product will give me the location, one location in this matrix. And I just multiply by this number, then you fill up the matrix, right? And then you just add sum over them. You have M, so you have sum over the row, sum over the column, then you will get the final matrix. I hope you can go back to practice this one more time, okay? But we already see that this M and N have some relationship. It is 0 if for the first term, if it is 0 if N is not equal to N. For the second term and third term, they need to have this relationship. M equal to negative N minus 1 or N equal to M equal to N plus 1, right? So I don't need to do a double sum in that case. I just need to do N equal to negative infinity to infinity. And then I plug in, right? I know that for my first term, it must be EC N squared N N. It needs to be N N. Because if it is not N N, I will get 0. For the second term, and third term, I have EJ divided by 2. And this time, it needs to be N plus 1 N. Or N minus 1 N to be non-zero. Right? The reason is that if you look at here, if M not equal to N plus 1, the first term won't be non-zero. It will be 0, right, for other values, unless M equal to N plus 1. So this is M equal to N plus 1, and then this is N, right? This is only non-zero is M equal to N minus 1, right? For the M, this is for M and row, right? So row is N, right? But need to be M equal to N minus 1. And that's why I have this summation. Maybe a lot of math, but okay, if it's too much, fine. I don't test this in the exam. I do have this in the assignment. Derivation, I don't test the derivation. I do have this in the assignment. You need to go through that, right? But later, right? But what we care about is now we only want to look at the two-level system, right? This was the equation I wrote earlier. Now I only have 2 levels. Let's say I only operate on 2 levels. This is wrong, depending on the region of operation, right? So this is an approximation, but it will be interesting to see whether this is correct. For charge qubit, this is correct, very accurate, right? But let's look at this. So for two-level system, what would that be? Summation, when I say two-level, I mean I only care about n equal to 1, 0 and n equal to 1. I only add these two terms, right? So I have, let's start with n equal to 0 is 4EC, right? I'm doing the summation, right? I add n, I put n equal to 0, right? 0 square, 0, 0, minus EJ, 1 over 2, 0 plus 1, 0, plus 0 minus 1, 0. That is for n equal to 0. Then I need to sum the second term, 4EC, 1 square, because now n equal to 1, 1, 1, minus EJ, 1 over 2, 1 plus 1, 1, plus 1 minus 1, 1, right? So here, let me mention this is n equal to 0, n equal to 1. How about n equal to 2? Do I need to do that? No, because I already said that I'm doing approximation. I only look at n equal to 0 and 1, right? Now, of course, what happened? This is gone, right? Because you multiply by 0 square. How about this one? This one is also gone. Because we say that we limit to 0. Here I have a negative 1 state. This is also gone. Why? Because I have 2 states, right? n equal to 2. So as a result, this is equal to 4EC 1, 1, minus EJ over 2, 1, 0, plus 0, 1. Right? Because this is 1 square, right? So I just put it as 1. This one is 1, 0, 1, 0. This is 0, 1, 0, 1. Right? Can I write the matrix of this one? Yes. I already told you what is the meaning, right, of 1, 1, 1, 0, 0, 1 outer product. You just refer to the matrix with that corresponding row and column. I just show you here as an example. 0, 1 will give me 0, 1. I have a 1 here, right? So you can go back to practice, but basically this is what you get. No 0, 0, so I don't have anything. Then this one I get EJ divided by 2, negative EJ divided by 2, 4EC. This is the Hamiltonian I have for the Cooper pair box I have created. An approximation. Is that correct? We don't know yet. But with this one, you plug into Schrodinger equation. You solve it, right? How do you solve Schrodinger equation? I h bar partial psi, and let me just make it very specific. Partial alpha beta partial t equals to this Hamiltonian times alpha beta. So now you have the matrix plug in. You have a system of differential equation. Then you can see how the alpha and beta will change, right? So you can get all the things that is important. But we won't continue. We will continue later. But the main point here is that we have developed the Hamiltonian quantized version, right, for the Cooper pair box, which means you have a Josephson junction and a capacitor, just like the LC tank, but now it's Josephson junction and capacitor. And we represent it in the lumber and phase operator, lumber and phase operator. And then we also represent the matrix in the eigenvector of the lumber operator. And we can solve it. Now, here if this one works well, what is the meaning of this qubit? this qubit can have n equal to 0 level or n equal to 1 level. What does it mean? It means, if you look at this circuit, I have 0 over 1 extra Cooper pair. Or you can say I have 0 over 1 Cooper pair tunneling through this Josephson junction into this island. Right, so basically just like I have a room, I have 1 or no person, or 1 or no extra student in our class. And you know we can have a superposition, right? So these are the basis state. And basically we're playing with the superposition of 0 and 1 extra pair of Cooper pairs. Right? If you use the classroom as an example, I have 0, I have superposition of 0 and 1 extra student for this semester, if we can quantize this classroom. Right? So that is what we have done, but we have not solved anything yet. So now I want to move, any questions? We'll revisit the solution again. The math is a lot. You need to decide how deep you want to go in. I won't test all this derivation. I try not to. Even I test, I will give a lot of hints because it's not the purpose of this class, right? But you should be able to understand this matrix.